Hello everyone. We all know that the virtual oscillator control is an emerging decentralized control method for grid forming applications. Today we are going to see the simulation of one of the first developed virtual oscillator control, that is vendor Pol Oscillator Dynamics based grid forming controller that we can use for the parallel operation in microgrid. The converter control using a vendor Pol oscillator is suggested to advance the development of nonlinear oscillator based control techniques. The van der Pol oscillator is one of the particular member of the family of weakly nonlinear Leonard type of oscillators. This van der Pol oscillator serves as the foundation for the majority of present application of virtual oscillator controls. So this is the schematic of virtual oscillator dynamics based parallel three-phase inverters. So we have DC voltage source of 750 volt, and then we have voltage source inverter inside with the controls, and we have this measurement line, and that is become called it as bus. And then we have line impedance whose parameters are set as r line 1 and l line 1. And then we have this measurement post line, and then we have two loads are connected at the PCC, and we are giving this load disturbance at time t equal to 2.5 second, and we are increasing the load by 8 kilowatt and 2 kVAR, and again we are switching off the load at t equal to 3.5 second. And similar with this first voltage source inverter structure, we have identical voltage source inverter structure too. So this one is voltage source inverter 2, and then we have measurement line, then we have line impedance, and we have this measurement post line, and then this is three phase circuit breaker, and load impedances are set as like this one. So let us go inside this so let us go inside this voltage source inverter 1. So we have this universal bridge. So all the parameters are set as by default, and we have this LCL filter whose parameters are set as RC, LC, this converter size, inductance and resistance, and then we have damping resistor and capacitance, and then we have grid side inductance and resistance. Now we are first sensing this inverter output current, that is I inverter 1 IAVC, and we are converting this inverter current from AVC to AVC component to alpha beta component, and we are using only alpha component, and we are feeding it to this current gain Ki value and providing it to this vendor Pol Oscillator Dynamics. Inside the vendor Pol Oscillator Dynamics, we have LC resonant tank, and we have these two control current source. In one control current source, we have input this current gain, and another current source we have input is alpha VCQ, and VC is the voltage across the capacitor of VdPO circuit. And we have variable resistor whose value is set as by default, minimum resistance is by default, and we are providing the input as R equal to -1 by sigma. So its value we are given in the MATLAB script file, so it will come from there. In earlier MATLAB version, you can directly use this resistance branch, but and set this value as R equal to -1 by sigma by changing by having the opposite polarity. But in this updated MATLAB version, you have to use this variable resistance to have the negative resistance value. So this is very important. In the current updated MATLAB versions, we have to use this variable resistance to apply the negative resistance value. And now the output of vendor oscillators, that is capacitor voltage and inductor current, are scaled up. So capacitor voltage is scaled up by voltage gain kV, and inductor current is scaled up by omega L into kV. And this after scaled up voltage and currents, we are providing to this rotational matrix, and rotational matrix is given inside this MATLAB function. So this is the rotational matrix script. In rotational matrix, you set phi equal to pi by 2 for conventional and phi equal to 0 for opposite group equations. Now we convert this alpha beta component as ABC component, and after dividing through this VDC by 2, we get the ABC modulation signal, and that we feed to the PWM generator, and whose frequency is set as FSW, and sampling time is set as 2.5 microsecond. So this is all for the schematic of voltage source inverter. So you can see this schematic of voltage source inverter 1 that is run through this Pol Oscillator Dynamics. Now let us see the some important points about Pol Oscillator Dynamics before we see the simulation results. And also this voltage source inverter is identical to this voltage source inverter 1, and all the parameters are set, our parameters are identical with respect to voltage source inverter 1. So let us see some important points about VdPO dynamics. So the Pol oscillator is used as the base for VO control because it can produce a stable limit cycle oscillations. The nonlinear second order differential equation of Pol oscillator is given by this equation, and this is the electrical schematic of Pol oscillators. We have a resonant tank with two dependent current source, and we have this negative resistance element. So this composed of parallel connection of harmonic oscillator with inductance L and capacitance C yielding resonant frequency a negative conductance element minus sigma in nonlinear cubic voltage dependent current source alpha VCQ. This circuit represents a narrow band pass filter where the resonance frequency is amplified. This resonance frequency set as 50 hertz, means whatever the grid frequency you want to set, you set this resonant tank with that value. These oscillations can be used as voltage source reference for the PWM generator. And this is the block diagram of virtual oscillator control for a DG converters. The dynamics of VO inductor current and capacitor voltage are this one. So if you want to write the virtual oscillator in the equation form, mathematical equation form, you can have this equation 1 and 2, and you just write this in mathematical form, and you can generate the PWM pulses with the help of this dynamics of virtual oscillator control. This virtual oscillator control is coupled to physical electrical signals in the converter through the voltage and current scaling gains kV and Ki respectively. And how we design the VO control? The input current decides the amplitude of oscillation voltage. The gains kV and Ki determine the scaling between converter terminal voltage and current with virtual oscillator circuit as kV we set as reference voltage and Ki set at 3 into V minimum upon P rated. The orthogonal oscillator scales states that the capacitor voltage inductor current are scaled by kV and omega L kV respectively and pass through the rotational matrix to get the voltage command in the alpha beta frame. The terminal voltage can be measured by RMS amplitude V and phase angle theta by using these equations. And now how we set this virtual oscillator control parameters. So beginning with the droop control equations, we know that DG converters are operating in reverse droop because we have set it for the distribution system. So this value are coming this one in PI and MQI, and this VO control is designed to emulate the same steady state droop control. So you can correlate, you can get the identical value of droop coefficients. The values of sigma and C depend upon the droop coefficient. So you will get the identical droop. You can get the identical droop gains with the help of these equations. The oscillator voltage oscillator grid frequency which decides the value of inductance. Now this one is very important slide. This Pol Oscillator Dynamics based virtual oscillator control is not nowadays being recommended to use for the application of grid forming converter because there are various limitations of VdPO dynamics over other oscillator dynamics, and these are: first is presence of load or harmonics, second is absence of power set points. There is no power set points, so you cannot dispatch power according to your wish, and it's share power based upon the converter ratings, and it may become unstable uh, if having some improper power set if having some improper droop coefficient value set for the converters. Design trade-offs that impede dynamic performance, that it is trade-off between harmonics, mainly third order, and transient performance. It has limit cycle restriction, a stability issue due to initial condition, and guarantee synchronization condition. So these are the limitation of VdPO dynamics over other oscillator dynamics, that due to which these oscillator dynamics is will not recommended for the use of application of grid forming converter. So nowadays we have other oscillator dynamics like AHO dynamics, unified virtual oscillator dynamics, and dispatchable virtual oscillator dynamics. So these are being these are having uh, used for these grid forming applications. Now let us see the simulation result. So first we will see this power sharing simulation results. So we can see this power coming from the two converters that are having identical, because we have set the identical parameters, and we have, so you can see both powers are overlapped to each other, and top one is for active power and bottom is for active powers. So you can see both are overlapping to each other. Now we can see this frequency response. Frequency response is faster, but it has some oscillations due to non-linear oscillator dynamics. And you can see this frequency drops when power demand increases. And let us see this load bus voltage. So this is load bus voltage, and there is some drop in the magnitude at when we have increased load demand. So this is the PCC voltage we have seen. Now inverter output current, you can see both inverters are sharing power equally, and both increase their power output when the power demand increases. And this is the current sharing. So this current sharing also overlaps to each other, because both inverters are sharing power equally. So this is voltage synchronization. Both converter voltage are overlapping to each other. And top one is this is RMS voltage. This red curve is RMS voltage output. So that's all. Thank you for watching this video. Thank you. So before that, I would like to tell you that I will provide this uh, a script file in the description box. So here I have written all the parameters that I have used for this MATLAB simulation, and I have kept in this MATLAB script file, and I will provide this in description box. And if you have any doubt, you can ask in the comment box. Thank you.